So we have a situation which has concerned with the diesel cycle. Let us go through the entire situation and then let us see how we can proceed with the solution of this problem. So we have to calculate the percentage loss in the ideal efficiency of a diesel engine. So we are talking about the ideal cycle with compression ratio 14 if the fuel cutoff is delayed from 5% to 8%. Now let us first understand what they mean by the delay in the fuel cutoff and how it will affect the efficiency. So let us understand something about this and then we will calculate whatever they are asking. So let me show you here a diesel cycle. So there is a diesel cycle I have drawn on the PV coordinates. This is the pressure axis, this is the volume axis. Now if we see the basic processes of the diesel cycle, starting from 1 we have isentropic compression, reversible adiabatic compression 1 to 2. Then 2 to 3 constant pressure. In the ideal diesel cycle there is a constant pressure of heat addition. So constant pressure heat addition takes place from 2 to 3. So this is heat addition at constant pressure, and then the heat addition is cut off. That means there is no heat being added. In the actual diesel engine, this corresponds to the spray of the fuel injection in the cylinder. Then the 3 to 4 is the isentropic expansion, that is reversible adiabatic expansion, and 4 to 1 is the constant volume heat rejection. This is the constant volume heat rejection. Now they are saying what will be the effect in the efficiency if the fuel cutoff is delayed from 5% to 8%. Now 5% to 8% of what? What is the 5% and what is the 8%? What they want to say through this problem is that the fuel cutoff 2 to 3 which is taking place, it is 5% of the swept volume or the stroke volume. So 1 to 2 is the stroke volume. This is, if you see in the problem 1 to 2, this is the entire stroke volume. This is called as VS, stroke volume or the swept volume, when the piston moves from top dead center to bottom dead center or bottom dead center to top dead center. Fine. So this is the position of the piston which is bottom dead center, it is called, and this is the position which is top dead center. Fine. Now we can say that 1 to 2 is the compression and 2 to 3 is the heat addition. That is what they are talking about. 5%, 2 to 3 is 5% of the swept volume or the stroke volume. This is the clearance volume which is VC. Now what initially we have is, initially we have V3 minus V2. This is the volume during which the fuel injection or the heat addition takes place, divided by V1 minus V2, divided by V1 minus V2. This is 5%. So this is 5 upon 100 if we talk in terms of fraction, right? Now also we can say that this is changing to 8%. they are saying this is changed from 5% to 8%. So changing from 5% to 8% means what? It means that now the heat addition will not take place from 2 to 3. It will further extend and it will further move to, let us say, 8%. So let me just mark this here. Let me just mark this here. So it will be like this. It will be like this, and then let us say 2 to 3 dash it is taking place. So this takes place, for example, 2 to 3 dash, and then from 3 dash to 4 dash there will be isentropic expansion. So from 3 dash to 4 dash we have the isentropic expansion, and from 4 dash to 1, from 4 dash to 1 we have the constant volume heat rejection, right? So for the new cycle we will have V3 dash minus V2. This volume is the volume of the fuel injection or the heat addition at the constant pressure, and this upon the stroke volume is equals to 8%. So what is the effect on the efficiency if we change from this to this? Compression ratio, they are saying compression ratio R, that will remain same, because that depends upon the volume ratio V1 to V2. V1 upon V2 is the volume ratio, and this remains same to 14 they have mentioned. So this will be 14. Now let me talk about one or two things, and then we will solve whatever they have given. If we see here in this situation, so the ratio of the volume from 1 to 2, the ratio V1 upon V2 is termed as R. The ratio V1 to V2, this ratio is termed as R. So we have this ratio as R, that is the compression ratio. Then we have the ratio from 2 to 3, or for the changed cycle from 2 and 3 dash. So volume ratio V3 upon V2 is called as the ratio which is the cutoff ratio, the ratio of the volume where the cutoff takes place and the volume where the fuel injection starts. So we denote it with the, I am denoting it with rho. Somewhere it is written as RC, cutoff ratio. Fine. So from 3 to 4 is the expansion ratio. So this 3 to 4 is the expansion ratio, and this I am denoting as RE. RE. This is the expansion ratio. So this is rho, or somewhere it is also denoted as RC. Now we should remember there is a relation, very important relation, because we are discussing this. So we should remember this relation, that R is equals to, how I remember this? This is the bigger one, from 1 to 2 is R. So this will be counted by these two, 2 to 3 and 3 to 4. Counted by means just a way of understanding. So if we are moving from here to here, this ratio is R. So this R will be equal to rho into RE. So this R will be equal to rho, that is the cutoff ratio, into RE, that is the expansion ratio. So this is the compression ratio, this is the cut-off ratio, this is the cut-off ratio. Wherever we require, we will be using it, and this is the expansion ratio. This is the expansion ratio. And then we will have the diesel cycle efficiency. We can write the diesel cycle efficiency eta, and this expression of diesel cycle efficiency will be equal to, it is related with the, there are the terms of the Otto cycle efficiency are common here. So first let me write those terms which are common with the Otto cycle efficiency. So 1 minus 1 upon R is the compression ratio, whole to the power gamma minus 1. So these terms are common with the Otto cycle efficiency, but we have some more terms here. So this into we have the rho, that is the cutoff ratio, to the power gamma minus 1 upon, this is the gamma into rho minus 1. So if we include this term also, this into this term also, then it becomes the diesel cycle efficiency. If we do not include this term, only this term is the Otto cycle efficiency. Fine. So now let us find out the efficiency. So we have to find out the percentage change in the efficiency. So for finding out the efficiency, we should know R, we should know rho, that is the cutoff ratio, and we should know gamma. So let us see if we know these things. We know the compression ratio R, that is given to be 14. That is given to be 14. And there is no mention of gamma in the problem. They have not mentioned. So we will take the standard value of the gamma, that is 1.4. So we have R is equals to 14. We have gamma is equals to 1.4. And we know, this is the given data, V3 minus V2, and we know V3 minus V2 upon V1 minus V2 is equals to 5 upon 100. This is 5 upon 100. Now on the left side, if I divide with V2 in both numerator and denominator, we will get V3 upon V2 minus 1 upon V1 upon V2 minus 1, and this is equals to 5 upon 100, that is 0.05. Now V3 upon V2, if we see V3 upon V2, V3 upon V2, this is the cutoff ratio rho. V3 upon V2, this is rho. So this is rho minus 1 upon V1 by V2. So V1 by V2, V1 is this and V2 is this. V1 by V2 will be equal to R, that is the compression ratio. So this will be equal to R, that is the compression ratio, R minus 1 is equals to 0.05. Fine. Now for the initial efficiency, I can find out this, the cutoff ratio rho can be easily found out. So we can say this can be easily found out. Let me try to find out this value. So rho minus 1 upon R compression ratio is given to be 14 minus 1 and this is equals to 0.05. So I can find out the value of rho, that is the cutoff ratio initially. So let me find out this value, let me calculate this value. So this is coming out to be 0.05 into, we have this 14 minus 1 and this is plus 1. So we have 0.05 into 13 plus 1. So we are getting this rho is equals to 1.65. This is the initial cutoff ratio. Fine. So we have the initial cutoff ratio, rho is coming out to be 1.65. Now we can find out the efficiency term. Let us find out the efficiency when the cutoff ratio is 1.65. So we have the efficiency of the diesel cycle. This is equals to 1 minus 1 upon R to the power gamma minus 1 into rho to the power gamma minus 1 upon, this is gamma into rho minus 1. So let me keep these values. So we have the diesel cycle efficiency is equals to 1 minus 1 upon R. R is the compression ratio, that is 14. So compression ratio to the power 14 whole to the power gamma, that is 1.4 minus 1 into, we have rho, that is the cutoff ratio, this is 1.65 to the power gamma. So 1.65 to the power gamma, that means to the power 1.4 minus 1 upon gamma is 1.4 into rho is 1.65 minus 1. Sometimes in the problem they themselves give a value of Cp and Cv that is different from whatever are the standard values of the air. So in that case we should divide Cp by Cv and calculate gamma ourselves. So that is what we have to do. So diesel cycle efficiency, this will be equal to, so let me find the value of this diesel cycle efficiency. So this is coming out to be 1.65 to the power 1.4 minus 1. So we have 1 minus 1.0159 upon 0594 upon, so let me multiply with this 14 to the power, this is 0.4 and this is into 1.4 into, we have 0.65. So this is 2.61512. So now we can find out the value of efficiency. So we have this 1.01594 divided by, we have this and this 1 minus this answer. So we are getting the efficiency of diesel cycle is coming out to be 0.6115. Now this is the efficiency of the diesel cycle for the initial case which they have given. We can find out the efficiency when the ratio changes to 8 or the stroke, the cutoff ratio, cutoff volume is the 8% of the stroke volume. So now this is what we have to find out, 8%. Now for this 8% we can write this further. Further I can write for the second case, I can say V3 dash minus V2 upon V1 minus V2 is equals to 8%. So 8 upon 100 it will be. Now if we divide both numerator and denominator with the value of V2, we will be getting V3 dash minus V3 dash upon V2 minus 1 upon V1 upon V2 minus 1, and this will be equal to 0.08. So we have this. Then we can say further we can say that, so let me calculate it here further. So we have this V3 dash upon V2. So V3 dash upon V2, it will be V3 dash upon V2, it will be rho dash, the cutoff ratio, a new cutoff ratio, rho dash will be there. So we will have this equal to rho dash. I am writing it here. Let me write it here. So we will have this. This will come out to be rho dash minus this is 1 upon, we have this is V1 by V2, this is R minus 1, and this is 0.08. So further now we can say that this we have to find out, rho dash minus 1 upon R. R is 14, that is the compression ratio, minus 1 is equals to 0.08. So from here we can find out the value of rho dash. Rho dash value can be found out. I have directly calculated it, 2.04 it is coming out to be. The value of rho dash is coming out to be 2.04. Let me just do these calculations. So 0.08 into, we have 13 plus 1, 2.04. Now if the rho dash is known, we can find out the efficiency. So we can find out the efficiency for the diesel cycle, that is the changed efficiency. It will be equal to 1 minus 1 upon R. R is 14 to the power gamma minus 1 is 1.4 minus 1 into rho to the power gamma, that is 2.04, whole to the power gamma, that is 1.4 minus 1 upon, we have gamma, that is 1.4 into rho, that is 2.04 minus 1. So we have this. So efficiency of diesel cycle, the changed efficiency of diesel cycle we will be getting. So let me write the changed efficiency value. So this also I have found out, it is coming out to be 0.59. I am directly writing the value, you can calculate this, it will coming out to be 0.59055. So we have the changed efficiency, which is obviously lesser than the initial value. So the changed efficiency we have got, and if we have to find out the percentage change, the percentage, and what they have asked the decrease, I think, the calculate the percentage loss in the ideal efficiencies. They already know that it is going to be a decrease, it is going to be a loss. So we will calculate the percentage loss, So percentage loss. So what I will do is, I will write the initial efficiency minus the changed efficiency compared with the initial efficiency into 100. So this will give me the percentage loss. Whenever we have to calculate loss or gain, it is always calculated with reference to the initial value. So we have this initial value, and this initial value of efficiency, when we calculated, it came out to be, we calculated 0.6115. So it was 0.6115 minus, we have eta dash, that is the efficiency for the diesel cycle, 0.59055. So 0.59055 divided by the initial value, that is 0.6115, and this into 100. So we have this. So we can find out 0.6115 minus 0.59055. So divided by 0.6115 into 100. So this is coming out to be a loss of 3.42 percentage. So we have the loss of percentage, that is coming out to be 3.426 percentage. So this is the loss. So we have found out the loss in the efficiency if we increase the cutoff ratio, rho. Now, I have already discussed the entire problem. I will show you one by one the parts of the problem which we have discussed, so that if you want you can note down it. So, let me just show you initially. This is the problem which we discussed. This is the problem. Then I discussed the problem was discussed, and then I discussed this part. This was the given data. Let me just slightly minimize it so as you are able to see it on a single screen. So, this was the given data, and this is the discussion, extra discussion which we did. You can go through this. And then we started solving this problem. So, solution is from here onwards. Here onwards is the solution. This is the first part of the solution. Then this is the second part of the solution.